For more than 350 years, a single problem stumped the world of mathematics. The problem was extremely simple to state, yet it proved fiendishly difficult to prove. Bounties were placed on finding a solution to the problem, and yet many people failed to prove it. Finally, in 1994, seemingly out of nowhere, a proof was offered. But it was a far cry from the initial promise of being simple. Learn more about Fermat's last theorem and its legacy in the world of mathematics on this episode of Everything Everywhere Daily.
Decisions.
Wait a minute. Are you still looking for cars on Carvana?
Yeah, decisions.
When I used Carvana, I found the exact car I was looking for in minutes. Bought it on the spot.
Electric or full diesel? Decisions.
Come on, you've been at it for weeks. Just buy it already.
You're right. Crossover it is. Decisions decided.
Whether you know exactly what you want or like to take your time, buy your car the convenient way with Carvana.
Want to shop Walmart Black Friday deals first? Walmart Plus members get early access to our hottest deals. Join now and get 50% off a one-year annual membership. Shop Black Friday deals first with Walmart Plus. See terms at walmartplus.com.
I've done many episodes on mathematical subjects, and I actually like doing mathematical episodes. However, there's a problem with episodes about mathematics. There are some topics that are difficult to do in an audio format. Most topics require a graph or at least an equation to illustrate what is being discussed. Moreover, there's a large gap in knowledge of mathematics among the listeners of this podcast. Some listeners consider themselves to be horrible at math and have never bothered to study it beyond high school. And I also know that there are professors of mathematics who listen to the show. The result is that there are some topics I would love to do episodes on, but I really can't because I don't think this is a good platform to do it. For example, in the year 2000, the Clay Mathematics Institute published 7 unsolved problems in mathematics. For each solution, they offered a $1 million prize to the person who could solve it. I've been thinking about doing an episode on this topic for over 4 years. And I'm not sure that I could possibly do it justice in the limitations of this podcast format. I'm not sure how to explain many of the problems, and to be honest, despite having a degree in the subject, there are some of the problems that I don't completely understand. Many of the great unsolved problems today are in obscure branches of mathematics and are difficult to comprehend if you don't specialize in that field. The subject of this episode is much more approachable. It harkens back to a time when mathematics was just being formalized, and it became one of the earliest and most famous unsolvable mathematical problems. And it starts with Pierre de Fermat. Fermat, born in 1607, was a French mathematician, lawyer, and government official, widely regarded as one of the founders of modern number theory. Born in Beaumont de Lomanie, France, Fermat worked as a lawyer and magistrate, but pursued mathematics as a passionate hobby. His contributions to mathematics include the development of analytic geometry alongside René Descartes, early work on calculus, and foundational contributions to probability theory with Blaise Pascal. Fermat is most famous for his work in number theory, particularly the subject of this episode, which has become known as Fermat's last theorem. The origin of this theorem goes back to one of the oldest theorems in mathematics, the Pythagorean theorem. The Pythagorean theorem states that in a right triangle, the square of the hypotenuse, aka the side opposite the right angle, is equal to the sum of the squares of the other two sides. Expressed algebraically, it would be a squared plus b squared equals c squared. An example of this would be 3 squared plus 4 squared equals 5 squared, or 9 plus 16 equals 25. In this case, 3, 4, and 5 are known as Pythagorean triples. And it turns out that there's an infinite number of Pythagorean triples, where a squared plus b squared equals c squared. 5, 12, and 13 are another set of Pythagorean triples. 5 squared plus 12 squared plus 13 squared is 25 plus 144 equals 169. The Pythagorean theorem is part of a more generalized type of equation known as a Diophantine equation. They too have an ancient origin. They're named after Diophantus of Alexandria, who wrote the early mathematics text titled Arithmetica, which explores solving algebraic equations, particularly Diophantine equations, focusing on rational or integer solutions. In the Arithmetica, Diophantus talks about how a square can be split into two other squares, as in the Pythagorean theorem. In Fermat's personal copy of the Arithmetica, he makes a short observation in the book's margins written in Latin. The translation of what he wrote into English is as follows, quote, "It is impossible to separate a cube into two cubes, or a fourth power into two fourth powers, or in general, any power higher than the second into two like powers. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." End quote. Basically, Fermat claimed that instead of raising numbers to the power of 2, like in the Pythagorean theorem, if you raise numbers to the power of 3, 4, or any other number, it would be impossible. Moreover, in what turned this simple claim into something legendary, he said that he had found a way to prove it. Fermat died in 1665, and 5 years after his death, his son published a new edition of the Arithmetica, which included his father's notes. It was this copy of the Arithmetica with Fermat's notes, which is how Fermat's last theorem came to the attention of the world, and why it was named his last theorem, because it was released after his death. The simplicity of the theorem statement, combined with the mystery of Fermat's missing proof, attracted mathematicians for centuries. Fermat himself actually took the first step in attempting to solve this problem. He proved that the theorem was true for any integers raised to the power of 4. One consequence of Fermat's proof was that it proved the theorem for every even exponent, and this whittled down the problem to just proving it true for all odd prime numbers. The next major step took place almost a century later with the great Swiss mathematician Leonhard Euler. Euler proved the theorem was true for all values of 3. Technically, his proof contained an error, but that was later corrected by others. Again, it wasn't a general solution to the problem, but if the general theorem was true, then it also had to be true for the number 3. The biggest advance in tackling the problem was made in the early 19th century by the French mathematician Sophie Germain. Germain approached the problem by introducing what is now referred to as Germain's theorem. She demonstrated that if p is an odd prime and 2p plus 1 is also prime, then there are no solutions for such numbers. And this was a huge step beyond what Euler proved because it covered an infinite number of cases. For example, her proof covered Euler's proof of 3 because 3 times 2 plus 1 is 7, which is prime. And it also proved 5 and 11 for the same reasons. However, it did not provide a proof for 7. Germain's work was groundbreaking and earned the respect of leading mathematicians of the day, such as Carl Friedrich Gauss. However, in her correspondence with Gauss, she used a male pseudonym because she didn't think she'd be taken seriously as a woman at that time. In the late 19th century, German mathematician Paul Wolfskill left a substantial prize for the first correct proof of Fermat's last theorem. This reward inspired a flood of submissions, all of which were invalid. Wolfskill himself had become interested in the theorem after thinking that he had found a proof, but later realizing his error. Thousands of incorrect proofs were submitted attempting to claim the prize. What really changed were modern advances in number theory which were developed in the 20th century. And one of the developments was elliptic curves, and the other was called modular forms. In the 1950s, a conjecture known as the Taniyama-Shimura-Weyl conjecture was proposed. This conjecture suggested a deep connection between elliptic curves and modular forms. Though seemingly completely unrelated to Fermat's theorem, it became central to its proof. That's because in 1986, Kenneth Ribbett of the University of California, Berkeley, proved that if the Taniyama-Shimura-Weyl conjecture was true, then Fermat's last theorem also must be true. And this shifted the problem to proving the Taniyama-Shimura-Weyl conjecture. Now entered into the picture Andrew Wiles. Wiles was a British mathematician who developed a passion for mathematics at a young age and was inspired by Fermat's enigmatic theorem. He earned his PhD at Clare College in Cambridge and became a leading figure in number theory, specializing in elliptic curves and modular forms. He was working at Princeton when he read Kenneth Ribot's work and set out proving the Taniyama-Shimura whale conjecture as a means of proving Fermat's last theorem. Wiles worked by himself for years on the problem. In fact, he never told anyone other than his wife that he was working on the problem. And one of the reasons he didn't work with anyone else and never told anyone about it was because of the mystique that Fermat's last theorem held. There had been numerous amateur mathematicians who claimed to have solved the theorem, but actually really didn't understand it. Some conspiracy theorists claim that Fermat's original, quote, marvelous proof existed but had been lost or suppressed by the powers that be. These theories often involved no real mathematics and were purely speculative. Crank mathematicians sometimes resubmitted their proofs repeatedly, even after the experts had refuted them. The internet era amplified this, with forums and blogs hosting numerous amateur claims. According to mathematical historian Howard Eaves, quote, Fermat's last theorem has the peculiar distinction of being the mathematical problem for which the greatest number of incorrect proofs has been published. End quote. Finally, after years of isolated work, in June of 1993, Wiles announced his findings at a conference. He had done it using the modern techniques and proving the Taniyama-Shimura whale conjecture, which Kenneth Ribot showed would then prove Fermat's last theorem. However, there was something about Wiles' proof that most people didn't expect. When Fermat wrote in the margins of his book, he seemed to imply that his proof was short and elegant. Wiles' proof was not. It was over 100 pages long, and it involved a host of techniques that were used in modern number theory. The proof was extremely complicated, and it wasn't something that most mathematicians could quickly verify. Once mathematicians were able to take a look at his proof, by August of that year, several of them had found an error. He went back to the drawing board and went to work trying to fix the error in his proof. By September 1994, he was almost ready to give up, but he finally made a breakthrough, and on October 24th, he submitted 2 papers, one which was his main proof, and a second which explained his corrected original proof. They were both formally published in 1995. After 358 years, Fermat's last theorem was proven and was verified by the mathematical community. Andrew Wiles' work has had enormous implications beyond just solving this particular theorem. His work has helped advance many other related fields of mathematics. For his work, Wiles was named a Fellow of the Royal Society, was knighted, and in 2016 was awarded the Abel Prize, the equivalent of the Nobel Prize in mathematics. He was also given a special award by the International Mathematical Union because he was ineligible to receive a Fields Medal, which is one of the most prestigious prizes in mathematics. The Fields Medal is only awarded to mathematicians under the age of 40, and Wiles made his breakthrough at the age of 41. Fermat's last theorem was one of the longest unsolved problems in the history of mathematics. For several centuries, there were those who thought that Fermat's last theorem was impossible to solve. In fact, there was even an episode of Star Trek: The Next Generation, which was recorded 5 years before Wiles' proof, which had it still unsolved in the 24th century. When it was finally solved, its solution was in a form that no one expected. Ultimately, Andrew Wiles' 1994 proof succeeded because it was built on centuries of mathematical progress, demonstrating that solving such a deep problem required modern tools and techniques far beyond what Fermat or his contemporaries had available. And it also took an incredible amount of tenacity. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Benji Long and Cameron Kieffer. I want to give a big shout out to everyone who supports the show over on Patreon, including the show's producers. Your support helps me put out a show every single day. And also, Patreon is currently the only place where Everything Everywhere Daily merchandise is available to the top tier of supporters. If you'd like to talk to other listeners of the show and members of the Completionist Club, you can join the Everything Everywhere Daily Facebook group or Discord server. Links to everything are in the show notes.